Good morning. I'd like to thank sincerely the organizers of the Asia Communications and Photonics Conference, ACP, to invite me for this plenary lecture, which is a great pleasure and also honor to give this to you this morning. And I would like to talk about photonic chip-scale frequency combs. And before starting, let me mention that the work has been done with a number of collaborators, in particular the late Michael Gordetsky, but also in particular Sunil Bava from Purdue, John Bowers, Christian Coos, Tobias Hare, and Paul Seidler. And I'd also like to acknowledge my former members, in particular Professor Guo, who is now in Shanghai, but also many others who have contributed to the work I'm going to present today. Last, I'd also like to acknowledge my funding agencies that have made possible this work, in particular DARPA and the European Union, and also mention that I'm co-founder of Ligentech, a photonic integrated circuit foundry for silicon nitride. So I don't have to introduce much the concept of optical frequency combs, so I'll be very brief. They're really a revolutionary tool that was invented by Ted Henge and Jen Hall and came to fruition with the advances in photonic crystal fiber. And it allows to create these bidirectional links between the optical domain and the RF domain, and has been used in a variety of applications, including frequency synthesis, optical atomic clocks, and many others. Now, optical combs are commercial technology. They've been commercialized by Mendel Systems, where they have been utilizing kind of femtosecond fiber laser combs to generate optical frequency combs. And these systems, despite kind of being very, despite being, having many uses, they're still kind of comparatively rare. There's about 250 units been sold in like 15 years, mostly to metrology laboratories and labs that are fortunate to have the funds to buy these femtosecond laser combs. Now, over the last decade, there's been a lot of work on generating chip-scale optical frequency combs. And what I'd like to do is today is the following. I'd like to briefly kind of outline the underlying physics, and I apologize for those who are very familiar with it. And I just want to give one more time the key kind of physical principles that allow to generate chip-scale frequency combs, which is based on parametric interactions, which is a different kind of phenomena than you would utilize in a typical femtosecond laser where you have gain and central absorbers. And then for the remaining part of the presentation, I want to focus on two recent examples where we've used these microcombs in LiDAR. And I explained to you two different LiDAR techniques that we've engaged in. And then conclude by some outlook on what else can be done with the underlying photonic platform, the silicon nitride. So in order to generate optical frequency combs, the process that we use, my lab described first almost 15 years ago, called Kerr frequency comb generation. And in this case, what is done is when it pumps an optical resonance with a CW laser, and one has parametric fluorescence. So parametric fluorescence here is mediated by the Kerr nonlinearity of the glass, so the intrinsic native nonlinearity. And once this, the Kerr nonlinearity is a 4-photon process, or gives rise to a 4-photon process by which two pump photons are annihilated and a single and idler photon are generated. And because energy is conserved in the process, this gives rise to an equidistant pair of sidebands. Now, one important distinction to conventional laser, the threshold for this process scales inversely with the quality factor of the resonator squared. That means that a high quality factor can be used to dramatically reduce the threshold kind of this process before parametric oscillations set in. And conversely, it's imperative in any kind of microresonator frequency comb to achieve high quality factors. So this process can cascade and give rise to optical frequency combs. We demonstrated this, as I said, in 2007 for the first time. And kind of opposite to conventional femtosecond laser frequency comb, there's no central absorber here. So it's just a nonlinearity of the material that promotes the generation of these equidistant sidebands. Now, these Kerr combs over the last decade have really proliferated. Today, Kerr combs can be generated not only in silica devices with exceptionally high Q, but across kind of the photonic integrated platforms, ranging from silicon nitride, gallium phosphide, aluminum gallium arsenide, to materials that have both combined Chi2 and Chi3, such as lithium niobate, and also crystalline devices, or even diamond. Now, in contrast to conventional laser frequency combs, what's really unique here is one can achieve high repetition rate. In fact, it's much easier to obtain repetition rates on the order of hundreds of gigahertz compared to the low frequency range that is typically assessed by femtosecond lasers. And this has simply to do with the fact that the threshold for comb generation actually starts to increase with decreasing repetition rate. On the other hand, these high repetition rates of a few tens of gigahertz have applications that are very well suited and which require large repetition rates. One of them is coherent communications, which Christian Kuhs described. Another one I'll talk about today, which is LiDAR. But there are other applications such as astrophysical spectrometer calibration, low noise microwave generation, where being directly in a microwave repetition rate zone is actually highly advantageous. So now, despite this massive proliferation of platforms, let me just briefly mention there's another piece of physics that's needed to operate these microcombs. And that other piece of physics has to do with the fact that in a conventional microresonator, particularly if they're photonic chip-based, the quality factor is typically lower than some of these early devices that use crystals or reflown silica. And this means that this comb generation process, which I outlined in this very simple and naive picture of just simply cascading sidebands, is actually much more complex. Without going too much of the detail, it's now well understood how forward mixing happens in microresonators that have a finite cavity line width in the presence of finite dispersion. And what typically happens is that one generates nested combs. So frequency combs are generated, primary combs, which can then fill in via secondary forward mixing pathways. They can become incredibly complicated and populate one cavity line width, shown in gray here, with multiple frequencies. And that leads to a chaotic regime. So even though the optical spectrum on the spectrum analyzer might look perfectly fine, it generates an optical comb, the underlying waveforms are erratic. They have actually very low, the waveforms are not self-repeating in the cavity. They have very fast fluctuations. And that has been a roadblock in the early days of microcomb research for many years. And it can be overcome by making use of a very inherent property of any nonlinear driven system out of equilibrium, and that is pattern formation. And the pattern formation that we're using here was first described by my collaborator Tobias in my group about 7 years ago, and it leads to the formation of solitons. So despite having waveforms that are very chaotic and are generated in this complex forward mixing pathway, by appropriately tuning the laser frequency to a regime where the cavity becomes bistable, so where the intra-cavity field actually has two solutions, so where the Kerr frequency shift exceeds the cavity line width, one can generate and promote the formation of solitons. Now, these are so-called dissipative Kerr solitons. Dissipative Kerr solitons because the cavity has loss, and there's also here now a drive term that results actually from the pump power. So these so-called DKS, as they're now called in literature, form thereby spontaneously in this regime where the cavity is bistable, and provide access to a fully coherent optical frequency combs that can be very precisely modeled by this nonlinear driven and damped Schrödinger equation. So how does the generation of solitons function? So typically what one would do is one would take a laser, so the horizontal axis here is the detuning, the vertical axis the power, and one would tune kind of into the resonator. One will build up power inside the cavity. One would then hit the region where the cavity has so-called modulation instability, where it starts to generate sidebands. Okay, these are fully coherent, just like in the early comb spectra I showed in 2007, followed by a region of chaos, where all these sidebands lead to the promotion of further forward mixing products that lead to subcombs, and this leads to a chaotic region. The key that really unlocked many of the applications I'm going to talk about is shown here in green. That's a stable soliton generation. So if you tune the laser frequency further, there's eventually a regime where this chaotic waveform starts to stabilize and condense into a pulse train of solitons. And by appropriately changing the laser tuning, one can annihilate one soliton in the cavity at a time and end up in a state where only one single secant hyperbolic shaped optical soliton actually is inside the cavity. So this regime requires this kind of laser initialization procedure and operating with a laser red detune from the cavity resonance. So we can also kind of chart one more time these soliton states as a function of these two parameters, pump power on the vertical axis, detuning on the horizontal axis. And what we have understood in many other labs as well is how to operate in this regime where we can transition from an unstable modulation stability to this stable soliton regime. Now, one thing why I'm drawing this chart here, and I want to draw your attention early on, is that solitons can exist in a certain range of laser detunings. And I'll come back to this property when talking about FMCW LiDAR. So by changing the laser detuning, okay, in this regime, the soliton actually is retained, but the underlying carrier frequency is changed. And I'll come back to that point when talking about coherent LiDAR. So moving onwards, these solitons have also been observed now in many platforms, including magnesium fluoride, glass, silicon nitride, lithium niobate, silicon, and also in 3,5 compound semiconductors. And they give rise to fully coherent optical states that can span an octave. The window of solitons has been extended to both the visible but also to the mid-infrared. And they can operate with repetition rates as low as just a few gigahertz and as high as terahertz. So these solitons are not only interesting for applications, but also, and I want to mention this only with one slide, give rise to very intriguing nonlinear dynamics. And over the last years, my lab, but also other labs in the world, have really uncovered this nonlinear dynamics and this new phenomena that can be observed. And they range from crystallization of solitons, from so-called breather solitons and recurrence relations, to the generation of spatially multiplex solitons, as well as to dynamics that lead to the switching. Also, they have some very interesting nonlinear noise dynamics that has been observed actually to lead to a reduction of phase noise of a microwave drive and can be used as a nonlinear filter. Now, the platform that we have been particularly interested in to generate soliton in is our photonic integrated circuits. And about a decade ago, following some very beautiful work that came out of Cornell from the group of Michael Lipson at the time, Alex Gaeta, we focused on silicon nitride. And silicon nitride is a material that's very well known in the semiconductor industry. It's an edge-stop layer or diffusion barrier. But traditionally, it's been very challenging to make use of silicon nitride for integrated photonics because one needs to operate for microchromes in a regime of anomalous group velocity dispersion. And that requires a thickness of the silicon nitride of typically about 800 nanometer when operating at a telecom wavelength. Now, in order to overcome this, one can find ways to mitigate the stresses that are available in LPCVD as deposited films and create kind of crack-free structures. And my lab and also other labs now around the world have found ways to mitigate the crack formation and to generate integrated photonic circuits based on silicon nitride. Now, silicon nitride is really, I would say, a very interesting material for nonlinear photonics. It's the silicon of nonlinear photonics, so to speak. It's a material that has a transparency window from mid-IR to the visible range. It has a band gap of about 5 electron volts. It has a high effective nonlinearity. Put it into context, 10 times higher N2 compared to glass. Along with the smaller mode area that you have in these tightly confining waveguides, you arrive at an effective nonlinearity almost 2 orders of magnitude larger than optical fiber. Very critical for nonlinear photonics, you have no true photon absorption in telecom band, and the material is space compatible, which we demonstrated a number of years ago. So this makes this material really compelling, and one of the most important properties I'm going to describe to you today, but it's not inherent to the material, but it's extrinsic, is the losses. And I'll describe ways in which we can generate now exceptionally low loss photonic integrated circuits that operate just with 1 dB per meter loss. So you can generate solitons in these silicon nitride resonators. We've shown this in past work. So here is an example where we pump with 1550 nanometer a silicon nitride resonator. In this early work, this was still very high power with a few watts of CV. And we operate again in this bistable regime and can access a single soliton state. Now, 2 comments are in place. The first is that these solitons in these photonic integrated circuits can become very broadband. And so here you see, for instance, a soliton spectrum that covers almost 2/3 of an octave. So it covers all the telecom channels like the CL, O-band. In addition, we also observe here the appearance of dispersive waves. And these dispersive waves come from the fact that higher order dispersion terms become important. Now, I should mention that higher dispersion can be engineered. So by engineering the waveguide, one can also engineer the appearance of these dispersive waves. And one can, for instance, move these dispersive waves very close to the edges of the CNL band, for instance, if one is interested in coherent communication, or move them to F and 2F frequencies when one is interested to pursue an experiment for RF to optical links for frequency metrology. We have very good understanding of the underlying spectra. In gray here is shown a simulation based on the Sulato favor equation, and we have to include other terms like higher order dispersion, Raman effect, and thermal effects to fully describe the dynamics and also the spectral envelope of this of the solitons. Now, these silicon nitride frequency chromes have unlocked many applications for our lab and also other labs that we work with and groups in the world. So Christian Kuz already explained that after the discovery of the solitons and generation in silicon nitride, we used them immediately for coherent communications. The solitons can also be used for astrophysical spectrometer calibration, work we've done actually with Tobias here at CSCM, where these are pulse-driven and generate broadband spectra with repetition rates of tens of gigahertz that can be used to calibrate spectrometers that are used for the search of exoplanets. For the purpose of this talk, I would like to talk about the massively parallel coherent LiDAR approach, but also briefly mention that other applications are in neuromorphic computing, where one can use the optical chrome together with a photonic switching network to make very fast multiply accumulate operations and utilize the inherent property that a photodetector can perform an instantaneous summation, an analog summation of signals. And we've demonstrated that with Wolfgang Pernes and colleagues last year in a proof of concept experiment. So focusing on the coherent LiDAR, let me briefly mention kind of the technique that we're interested to apply microchromes to. Coherent LiDAR is a technique which is very similar to radar, where one sends out a frequency signal that is chirped. In this case, our chirp is triangular in nature, so our laser frequency is triangularly varied in time. And once the signal is reflected from an object, okay, the chirp is superimposed with the signal that's returned is superimposed with the original signal that's sent out on a photodetector. So it performs a heterodyne beat. And due to the fact that there's a time delay between the signal that comes back and the signal that went out, one can map the distance into radio frequency. And that's a key advantage because you're mapping distance into frequencies, and frequencies is a quantity that we can measure very precisely. Now this coherent ranging, also called FMCW ranging, has another very nice feature, and that is that if the object moves, it imparts a Doppler shift. And this implies that the original beat frequency, which is static for static objects, will show on the up ramp and down ramp a deviation, okay, and from this difference we can determine actually the radial velocity of the object. So for this reason, FMCW actually is perceived as a very interesting technology for long-range ranging of hundreds of meters, where the point cloud is sparse, so classification of objects becomes more complex and difficult. But it's been generally compounded by two aspects, that the technique requires very coherent lasers, coherence lengths of hundreds of meters. It requires very precise ability to chirp, to create a triangular chirp signal. Any uncertainty in the chirp will translate into uncertainty in the beat node, and therefore in a distance ambiguity or uncertainty. And the third aspect that this method has been compounded by is parallelization. Okay, current time-of-flight LiDARs use 128 parallel sources to obtain fast video rate imaging, and with coherent ranging with a single laser, the frame rates are typically much slower. Now here, the microchromes actually offer a very interesting and compelling solution because they allow to massively parallelize, okay, the FMCW coherent ranging. So what property do we use? We use a property that I alluded to already at the beginning of the presentation. If you look back into the stability chart, so laser detuning versus pump power, the green region is where solitons kind of live. Then what one can do is one can translate a laser, okay, from one detuning to another detuning within the soliton existence range. For silicon nitride, this existence range is quite large. It's actually several gigahertz. So that means one can achieve a resolution for coherent LiDAR that is just 2c over b, where c is the speed of light, b is the bandwidth, of typically tens of centimeters. So in this experiment here, we choose to operate at a detuning of 1 gigahertz and approximately 3 gigahertz and very fastly tune and chirp the laser. And one interesting aspect about solitons is, despite chirping the laser frequency very fast, the soliton still locks to the underlying carrier. And that means in frequency domain, what happens is that the entire optical frequency chrome is shifted, okay? So the carrier envelope frequency is acted upon, but the repetition rate to a very good degree of freedom actually stays the same, except for Raman nonlinearities that I won't go into detail of. So we've done this experiment. So this shows here the two detunings in blue and red. We use here the region centered around 1550 that we can amplify with the EDFA, and we have about 30 chrome channels. So in this experiment here, what we then do is we use our chirped pump laser. So the pump laser is chirped triangularly, and this triangular chirp is now transmitted to all the chrome lines simultaneously. So from a single FMCW laser, we now make a laser with more than 30 lines, and that inherit the coherence of the pump layers and also the chirp, except for some linearities that we understand very well due to the Raman effect. So this allows now to parallelize coherent LiDAR and therefore generates in an experiment multiple channels that can be dispersed with a grating, or in this case schematically shown here as a prism, and be used to parallelize the acquisition of FMCW coherent LiDAR data. And so we have done and shown a proof of concept of this experiment. So this is an example where we sent out the 30 beams, we dispersed them with a grating. We can also scan with a galvo in the orthogonal axis, and then in this case make a very simple experiment where we scan, for instance, in this case a logo of our university, EPFL in Switzerland. We can also retrieve distance information here of the target and the back reflector, and show here a resolution that is on the order of a kind of centimeter scale. So, so this architecture, if I just pause for a moment, has a number of compelling kind of advantages. It's first of all a truly parallel coherent LiDAR architecture that alleviates the need of using individual lasers. It can work both monostatic and bistatic, and by using multi-frequencies we eliminate any crosstalk that could happen to the interference of beams. Moreover, a general property of FMCW is that the technique actually is eye safe, and in particular the use of 1550 nanometer light, so a window that's strongly absorbed by or doesn't project actually on the human retina. So we can also perform imaging experiments, and again there's another example where we imaged here chess figures, and again we have here these more interior channels that we used. And again, the proof of concept ranging experiment in the lab with this parallel system. Now, one aspect that I have glossed over is that one still has, despite having achieved now a very compact source that has parallelized the generation of the carriers, the scheme I've just presented still requires a demultiplexer to measure each individual channel. And in principle, this can be done, and also done on chip with AWGs. But a very interesting question that one can ask oneself is, can one leverage the existing technology in coherent communications and telecom that operates with tens of gigahertz of bandwidth and utilize that for the low frequency bandwidth signals that LiDAR produce? Again, the signals I've presented in the last slide are typically 1 gigahertz in bandwidth that corresponds to a range resolution of a few centimeters, and it's typically required for long range LiDAR. So can one combine kind of the tens of gigahertz coherent communication detectors with coherent LiDAR happening at low frequency? And this, in fact, we have recently shown. And the idea here is to replace a demultiplexer with a single detector, a single IQ detector that retrieves the both quadrants of the optical field, and to make use of dual comb spectroscopy, to map each individual channel of the LiDAR signal into a different RF domain. And this can be easily also realized by using and employing a second microcomb. So what is the technique? The technique is the following. We used here in this case 2 microchromes. One microchrome again is our FMCW coherent LiDAR source that is parallelized as multiple channels. But now we use a second source which is also a solid microchrome that is also importantly chirped. So it also contains the same FMCW signal, but there's one very important distinction. This local oscillator comb in fact is offset. It has a frequency offset of the pump compared to the signal comb. In addition, and this is the second key aspect, it has a different repetition rate. And this different repetition rate here implies that you generate on a photodetector an interferogram. And each individual channel now is mapped to a different RF frequency. And that's shown schematically here on the left side here. So we have here a 0 frequency. You would have with the repetition rate difference times mu, the number of channels, you would have channels appearing at both positive and both negative frequencies. In this case here, this schematic shows the situation where the pump of the signal comb and the local oscillator comb in fact are degenerate. That's actually why they're two centered at 0 here. If you use an IQ detector, you can obtain both positive and negative frequency information and therefore recover all the FMCW signals that you've generated on the photodetector individually. So the key advantage of this approach is that it alleviates the need of multi-parallelized detection. One single detector is sufficient to record all the FMCW signals. So we've done this experiment. So we've taken two microresonator frequency combs with 98.9 and 99.4 gigahertz, so a slight offset difference here of the rep rate of about half a gigahertz. We generate the Salton frequency combs with two pump lasers at the same time. So one pump laser at the same time, so they pump the two resonators with different FSR, and we can nicely see here that if we now superimpose the combs on a photodetector, we can see the different RF frequencies. We see here channel number 3, which comes in at about 5 gigahertz, channel number 11 about 7 gigahertz, and we can therefore retrieve now each of the FMCW signals individually from the heterodyne beat node. Now with this we can perform a ranging experiment, and again we have also done this and shown it, but now again we only use a single detector, a single IQ detector to retrieve all the 30 channels in parallel. And in this case we have 28 channels that we are dispersed, and this leads to an aggregated pixel rate of 2.8 megapixels per second for 1D line scan. And just to put this into context, okay, a megapixel rate will allow, when also combining it with a two-dimensional scanning, so in the orthogonal direction, to attain video frame rate imaging of long-range LiDAR with 28 channels in parallel, which is very challenging to obtain with single sources. So even though what I've talked about a lot now is the underlying technology to generate the chirped combs, which was generated using lasers that can be very quickly and frequency agilely tuned. And I want to mention that one can also achieve very frequency agile tuning on chip by directly using onto the photonic integrated circuits piezoelectrics. And that's something we have explored with the group of Sunil Bhave. By directly integrating aluminum nitride as used for Wi-Fi onto the photonic integrated platform, we can achieve very quick frequency agility with frequency bandwidth of up to 10 megahertz, and thereby both have a voltage controlled Salton initiation and also voltage controlled chirping of the combs, which can be used for the FMCW that I've described. Now, despite these compelling applications that I've described of microcombs, I want to spend the last minutes here of my talk of talking about one very important ingredient in translating these findings to actual technological demonstrations, and that is the power requirement. So for many of the laboratory-based experiments, the power is not a concern, but for real applications in the field, power is certainly a concern, certainly when one talks about integration with 3-5 semiconductor lasers. And many of the applications of microchromes have been traditionally compounded by very high powers to initiate the solitons. Now over the last years, what my lab has been focused on is the fundamental question of the discrepancy between optical losses in fibers that are, have losses of a dB per kilometer. That's why we have the conversation today. Compared to integrated photonics, which up to a few years ago had losses of just at best a few dB per centimeter. And what I'll describe in the next slide is progress that we have made to take that loss from 1 dB per centimeter and reduce losses by about 2 orders of magnitude and move it to the level of dB per meter. And actually today, the photonic integrated circuits we have in our lab can operate with that level of loss. So we have 1 meter of path lengths we can wrap on a 2 by 5 millimeter chip with losses that are less than 3 dB. And that has very important implications for soliton generation, because this implies that the threshold for solitons will actually go down to just a few milliwatt. So how is this done? In a nutshell, we've developed and also patented a process that's called the Photonic Damascene process, where we have developed a new way to manufacture photonic integrated circuits. The traditional paradigm of manufacturing is using a thin film, taking photolithography and structuring the film. What we're doing here is a very different scenario, where we make a film with a pattern, okay, with a checkerboard pattern, or in this case a pattern for waveguides, a recessed structure, and then we fill that recessed structure with our waveguide material. And together with the reflow, this allows us to get exceptionally low optical losses. So this process, inspired by the copper Damascene process that's also used in VLSI interconnect, gives us the ability to make very high quality, crack-free and low propagation loss photonic integrated circuits based on silicon nitride that have losses of the level of dB per meter. So that allows to, and these very low losses in particular make use of one technique, which is reflow, which is to use the preform made from glass and slightly elevating the temperature where the glass softening transition occurs to take out any roughness from the etching. And that's why we can operate now virtually kind of roughness free in these tightly confining silicon nitride resonators, and have quality factors coming in that are as high as 13 million for a fully integrated tight confinement device. So with these low loss photonic integrated circuits, these are really a Rosetta Stone to many applications. Solitons can now be generated with just milliwatts of power. We can integrate the solitons directly heterogeneously or hybrid with refi pump lasers, and can therefore very widely access these soliton states. Now it goes without saying that these low loss photonic circuits have many other applications. So the silicon nitride that we've described can be used not only for making photonic chip scale frequency chromes, but also can be used to make continuous wave driven parametric amplifiers, which my group has recently shown. It can be used to make frequency agile lasers by combining with aluminum nitride piezo actuators, something we spun out in a new company called Deep Light, and it can also be combined with lithium niobate for making modulators, in addition to serving as efficient comb generators. Now the silicon nitride platform is commercial, so it's been commercialized by Ligentech. It's been used also by particular leading quantum computing companies like Xanadu. In fact, their recent quantum circuit with, on a nanophotonic chip actually showed here a Ligentech chip that was used for their experiments. So it also shows that this is now being picked up by quantum computing companies. For us, these low loss silicon nitride has allowed to access very low repetition rates. This is an example here of soliton microchromes that operate in the X and K bands, traditionally very challenging due to the power requirements. Here the power is only a few tens of milliwatt that we need, and they produce reasonably low phase noise signals here that are comparable to to commercial Rohde Schwarz signal generator.
3 minutes to go, Tobias.
Perfect. Yeah, I think I have 3 or 4 more slides, and this should be on time. So last, these low loss photonic integrated circuits also have allowed to close one important gap of soliton microchromes, and that's the pump laser. So we've shown that by directly injecting self-injection lock into a 3,5 indium phosphide DFB laser, one can not only injection lock and generate narrow line width from the DFB, but also operate in a soliton regime. And this shows here work that we've done with the late Mike Godetsky, where we showed a soliton self-injection locking regime that now gives rise to very, very compact comb generators. And this shows kind of work we've done with Tobias in the framework of a DARPA project, some of the most compact microchromes to date. This is our EPFL 15 gigahertz microchromes together with Freedom Photonics DFBs, fully packaged in a turnkey device that generates soliton pulse streams. So it shows that the technology is really maturing very quickly at a level where it can be commercialized. We can also achieve even heterogeneous integration, something we showed with John Barr's group earlier this year in a paper published in Science, where we show a fully kind of integrated microchrome operating in a soliton regime with heterogeneously integrated indium phosphide, silicon nitride, and silicon interposer layers. Now, last I want to mention that these exceptionally low losses that we have achieved in silicon nitride, along with the frequency agility of the photonic chips that we have added with aluminum nitride, has really opened the possibility to make very narrow line width low loss, very narrow line width lasers that have frequency agility that is significantly better than bulk lasers. And this is an example of recent work we did that's on archive, where we showed that we can make lasers with the coherence of a fiber laser, but tuning capabilities up to tens of megahertz. And these have particular applications in FMCW LiDAR, and are now also commercially distributed by our startup Deep Light that was founded earlier this year, that has demo units available of this novel technology, of this FMCW lasers. So with this, I'd like to conclude and say these soliton microchromes really have many applications relevant to both coherent communications, but also microwave photonics, spectroscopy, radar, clocks, and have over the last years really matured to a point where system level applications have been demonstrated, and transition into commercial products actually is foreseeable. With this, I'd like to thank for the invitation to speak here, and I'm happy to take any questions. I'd like to thank in particular our collaborators Christian Cruz and Sunil Bavel, with whom I've collaborated over the last years to make possible this work.